This is Dr. Hicks, and thank you for joining me for the Chapter 6 video lecture. To start off with a question that very similar to one that was worked out in the Chapter 5 lecture notes. Which temperature is hotter, 196 degrees Fahrenheit, 103 degrees Celsius, or 300 Kelvin? And I'll give you a hint. There's two ways that you could think about working this problem. One way would be to put all three temperatures on one scale and compare which is the hottest one. There might be a more clever way that you could reason through this based on some of the fixed points on those different temperature scales. But like usual, answers are at the very end. So Chapter 6 is all about waves and sound. Sound's a wave, light's a wave. So there's a lot of physical phenomena that fall under waves. So this is all the stuff that's in Chapter 6. The Doppler effect part, there's not a whole lot of that in the lecture slides. There's two YouTube videos in the folder with the Chapter 6 lecture slides. Those do a great job of really going into detail on the Doppler effect. So check those out for this. And then we'll wrap up by talking a little bit about standing waves and resonance. Right, so what's a wave? A simple answer is a disturbance. Better answer would be some disturbance that moves through a material from one location to another location. Medium is just another way of saying material. That material or medium could be a string. So if you whip a string like that, you're going to send a pulse down that string. That's a wave. Another way that you could think about this wave is that it's energy transferred by that disturbance. So if I whip this string and that pulse goes down the string, whatever that pulse hits at the end, that can transfer energy to something else. So these waves are going to generally transfer energy, but not mass. So ripples in a lake are the rings spreading out. Those are waves. Earthquakes are waves in the ground. Sound and light are both waves. So a whole lot of different wave phenomena around us every day. One thing that we need to watch out for here are electromagnetic waves. Those don't need a material to propagate through. They don't need a medium. What's oscillating here are electromagnetic waves. And we'll talk about that in a chapter coming up. So the way that we're going to classify our waves is essentially two broad categories. And those are based on how the material or medium is disturbed relative to which way the wave is actually moving. Okay, for longitudinal waves, the particle motion or the disturbance of the material is in the same direction as the wave. Sound's a wave. If I took a slinky, this isn't a slinky, it's a spring, but essentially a slinky. If I kind of stretch this out and send a pulse down it, the pulse is moving left to right, and so is the wave. That's a longitudinal wave. Kind of the opposite is like a wave on a string, where the wave is moving that way, but the string is moving up and down. The material movement up and down is perpendicular to the direction that the wave moves. That's a transverse wave. Light waves are transverse waves. The wave on a string is a transverse wave. Now, sometimes you can have situations where you have a mix of both longitudinal and transverse waves. Earthquakes do that. If you've heard of S waves and P waves with earthquakes, one of those is a longitudinal wave and the other is a transverse wave. And that's one of the reasons earthquakes can be so devastating, is you can have motion back and forth and motion up and down. So here's another cartoony example of a longitudinal wave. A particle displacement and wave direction are in the same direction. Rarefaction is just a fancy word for less dense. Transverse wave, the wave is going horizontally, but the particles are moving up and down. They're perpendicular. So now that we have a way of classifying our waves, we need to know some of the basic parts of a wave. The maximum displacement a wave gets, the biggest it moves away from being completely at rest. That's the amplitude. Amplitude is kind of a measure of the energy that a wave has. Now here, the distance from peak to the next peak, that's the wavelength. Wavelength is measured from one point on the wave to the next adjacent identical point. Peak to peak is an example of that. So is trough to trough or bottom to bottom. I could go part way down here to part way down over here. That's also a wavelength. A whole bunch of different ways that you could measure the wavelength on this wave. It's between two adjacent identical points. We use the Greek letter lambda as a symbol for wavelength. The time it takes for one complete wave to go by is called a period. Since period is time, the units for time are seconds. So period uses seconds for the unit. Frequency is kind of the inverse of period. So if period is the time for one wave, frequency is the waves per time, or waves per second. So it's essentially the inverse of the period. If you know the period, you know the frequency. If you know the frequency, you can find the period. Now, these come together, and this is kind of the important part. This equation here is just an example of doing speed is what? Distance divided by time, right? What's distance? It's wavelength. What's time? It's period. So I can use my speed equation from chapter 2 and rewrite it in terms of wavelength and period. Or, since 1 over period is frequency, you can also write this as that's frequency times wavelength. Another way of writing the wave speed equation. Okay, quick question for you guys. You tie a piece of ribbon to a stretched tight string and create a transverse wave on that string. How would you see the ribbon start to move? Would it be perpendicular to the wave, parallel to the wave? Neither of those are correct, or both of those are correct. Well, now let's work out a little bit of a more detailed example. So we are given that waves moving on a lake have a speed of 2.0 meters per second, and there is 1.5 meters between one peak to the next peak. We've got to figure out what the frequency of the waves is and what the period is. Well, the wave speed equation here, V is lambda over period. I could rearrange that so it looks like, so I do some algebra. The period is wavelength divided by wave speed. And that's useful because I know wave speed, that's the 2.0 meters per second. And I remember that I measure the wavelength from peak to peak or from trough to trough. So this 1.5 meters has to be the wavelength. So finding the period is just dividing wavelength by wave speed, and you get 0.75 seconds. Like I said before, if you know the period, you know the frequency, and we can get that from, so we already found the period. To find the frequency, we just do the inverse of the period. So 1 divided by 0.75 seconds. So that's 1.3, and I get seconds to the -1 power. That's the same thing as 1 divided by seconds. And that's the unit. I'm doing 1 divided by time. This 1 divided by seconds, that's a derived unit. And it's a simple derived unit, but it's important enough that it gets its own name, and that is a hertz. So this frequency that's associated with a 0.75 second period is 1.3 hertz. Okay, so let's talk about sound waves. The way that I generate sound waves is by compressing and expanding air. The way a speaker might do it is by pushing the speaker cone forward to compress the air in front of it. And then when the cone moves backward, it lets the air kind of expand, and it just does that very, very, very fast, and that makes a sound. The way that we're going to classify sound waves is by what frequencies most humans can hear. So between 20 hertz and 20,000 hertz is what we call audible. For most people, 20 hertz is very, very hard to hear. It's got to be really, really loud. 20,000 hertz on the high frequency side also has to be really, really loud for us to hear, if you can hear it at all. I don't think I can hear 20,000 hertz. Below 20 hertz is called infrasonic. Earthquakes are typically infrasonic frequencies. Some elephants can communicate through infrasonic frequencies that we can't hear. Above the higher end, so above 20,000 hertz, is ultrasonic. Bats echolocate at really high frequencies, some up to 150,000 hertz. Ultrasound machines that are used to image soft tissue in the body, those that use ultrasonic waves. We could also classify sound waves by speed, so how fast that sound wave moves in whatever material it's going through. And sound waves can move through more than just air. They can move through liquids or solids. If you listen with your ear up against the wall to hear something in the next room, you're hearing sound waves go from air through solids and back into air. Infrasonic frequencies of really low waves have a real long wavelength, and elephants can actually send those sound waves into the ground and use that to communicate with other elephants up to like 2 miles away. So they're not making that sound in the air, they're making the ground vibrate, and the ground can transfer those low frequencies way farther than the air can. So when we talk about light waves, we're talking about electromagnetic waves. So those don't need any material to actually vibrate. There's no medium required. You still have to have something oscillating, and those are electric and magnetic fields, which are recreated by electrically charged particles. Chapter 8 stuff. Visible light that we see, it's a very, very small part of this whole electromagnetic spectrum. So on the left side, we have really, really small wavelengths. That's 10 to the -5 nanometers. That is smaller than the spacing between atoms in a solid. Those are gamma rays. Very, very high energy, high frequency waves. Visible light's kind of in the middle. Really long wavelengths are radio waves. Those can be over a kilometer long. So really long waves have a really small frequency. So big waves are low frequency, short waves are higher frequency. So here's an example problem. How far does light travel in 1 year? And this works for any electromagnetic wave, not just a light wave. It works for a radio wave, because all of those electromagnetic waves travel at the speed of light. And that speed of light is a known constant, and it's 3 × 10⁸ meters per second. Really, really fast. So for this problem, we need to figure out how far light travels in 1 year. So I'm going to use the speed is distance divided by time equation, just like before, because I know my time, it's 1 year, and I know my speed, it's the speed of light. But I want to use it in the form distance is speed times time. So remember, there were 3 different ways I could write the speed equation. This is one of them. Distance is speed times time. So I know my 3 × 10⁸, that's the speed of light. I just need to know my time, and what is that? 1 year? That's kind of weird. So that's why there is this huge number circling in red for the time. So what we have to do is convert a year into seconds, because our speed is in meters per second. So the way that we do that, I'm not going to work out all the details here, but 365 days in a year, a day is 24 hours, an hour is 60 minutes, a minute is 60 seconds. So you got to go through year to day to hour to minute to seconds, and you end up with this many seconds in a year. So once I've got those conversions done, I just multiply the speed times the time, and I get a huge distance. And that's what you would expect if you have a very long time to travel, a year, and you can travel at an incredibly high rate of speed. So pause this video now. I would highly recommend taking a look at the Doppler effect supplemental videos first. I'm just going to do a very quick recap of that here. And that summary is essentially that you get the Doppler effect whenever a wave source and a wave observer are in relative motion with respect to each other. Either they're moving towards each other or they're moving away from each other. When they're moving towards each other, you get a Doppler shift to a higher observed frequency. We say that's blue shifted. Blue light has a higher frequency than red light. If the source and the observer are moving away from each other, then we get a lower frequency observed. And we say that's red shifted because red light has a lower frequency than red light. So things moving away, there's a Doppler shift to lower frequencies. Things moving towards each other, there's a Doppler shift to higher frequencies. This Doppler shift can be used practically, like with weather radar, Doppler radar, that measures the Doppler shift of a microwave radar wave reflected off of moisture in the atmosphere. And by measuring how much that reflected wave is Doppler shifted, the meteorologists can tell not only what direction the storm is moving, but with what speed. Here's the Doppler effect in pictures. This is a picture of a little sphere on an arm that can move up and down, and it's moving up and down in a big tank of water, just creating ripples of water. But this arm can also move left and right. So as it moves to the right, it makes these water ripples squeeze together. So there's shorter wavelength, higher frequency. And on the back, when it's moving away, you get the waves are stretched out. So there's a longer wavelength or a smaller frequency. Now, if you take that to the extreme case, where if this thing moving to the right can move exactly as fast as the waves are moving. So here the waves can still get out of this bar's way. But if the bar can move as fast as the waves, in that case, you'd actually have this water wave building up just all on top of each other, and you'd get a higher density region of water in front. If it's a jet, the jet pushes air in front of it. Eventually, there's a very high pressure region of air in front of the jet that actually has to kind of push through that to exceed the speed of sound. When that happens, that generates what's called a sonic boom. I used to live in a remote area of Wyoming underneath flight paths for some military jets, and we would hear sonic booms all the time. They would rattle the windows. And what's happening here in this picture, look at the top picture, fast moving plane, but still less than the speed of sound. Just like the water tank, in front of the plane, the air is compressed, but there's still gaps between those waves. Much faster moving plane is in the middle, moving at the speed of sound. All those gaps are right on top of each other, so you don't see them. And now, in the bottom one, the plane is exceeding the speed of sound, and you see those gaps, but now they're behind the plane. When that happens, this edge where these circles overlap, now that's the high pressure region of air, and that cone just kind of expands outward, and it's a shock wave, and that's what you hear as a sonic boom. This is a special picture of a jet moving at a high speed. This camera is sensitive to pressure differences, and it can actually image or take a picture of the shock waves coming off of this jet, and they're definitely form a cone. Same technology, different subject. This kind of looks like a boat going through a still lake. It's a bullet going through air, and you get a shock wave out front and a smaller shock wave out back and some turbulent flow behind it. Part of this shock wave is the loud sound you hear of someone, like the crack of a rifle. Part of that is the mini sonic boom that the bullet makes. If you crack a whip, that crack is the very tip of the whip moving faster than the speed of sound, and that creates a little pop or crack. That's what you hear. This duck swimming in a lake is also making a V-shaped wake with turbulent flow behind it. Looks a lot like this bullet. In this case, the duck is able to swim faster than the waves can get out of its way. it's essentially moving faster than the speed of sound in water, and that's another example of kind of like a sonic boom. You're not going to hear this because it's not a sound wave, but any kind of V-shaped wake is the object moving faster than the waves can get out of its way, which is the same physics as a sonic boom. Okay, question number 3. Here's a wave. What kind of wave is that? Longitudinal, transverse? Is it a sound wave or is it a slinky wave? It's not a slinky wave. Last thing I want to talk about are standing waves. And this is a special case of wave interference where you have a wave essentially interfering with a reflected version of itself, and that interaction leads to a wave that looks like it is not moving. So here is 3 different snapshots of a standing wave. There's videos. One of the videos with this chapter, the supplement of videos, is about standing wave. It's got really cool live pictures of this. Anyway, what you have are regions where this string does not move at all. Those are called nodes. In this middle picture, here's a node. You always have nodes at the 2 ends. The bottom picture is a more complicated standing wave where you have 2 nodes in the middle, and you still have to have nodes at either end. The places where you have maximum displacement, like in the middle, those are called antinodes. So whenever you pluck a string that's stretched tight between 2 points, it vibrates in a combination of all of these different patterns, including a 4 loop, a 5 loop, a 6 loop. They're all possible because you have the string fixed at both ends. These higher frequencies are multiples of this basic frequency where there's only 1 node at each end. This main frequency here is called the fundamental. When I pluck a string on this guitar, the sound that you hear is primarily the frequency associated with the fundamental. But this 2-loop standing wave pattern can also vibrate at the same time, and it's got a frequency that's double. So I would hear mostly that note, but there's a little bit of double that frequency mixed in. There's a little bit of triple that frequency mixed in. If I'm able to just kind of damp out those fundamental frequencies, I can make my guitar string vibrate and play and only hear the higher harmonics and not the fundamental. Another thing that's going on when I play my guitar is the whole box or the whole soundboard starts to vibrate and resonates with the strings that makes it louder. All physical objects tend to have several different frequencies that they vibrate more easily at. Those are called natural frequencies. Those are things that they want to vibrate at. When you push a kid on a swing, you time your pushes so that you only push when the kid is back as far as they can go. So your pushing force is resonating with their swinging. They're both at the same frequency, and that lets you couple a lot of energy into the kid's swinging. If you were to apply your push while they're still swinging back, that would cancel out and they wouldn't swing as much. That would be non-resonance. In this cartoony picture of two tuning forks, if they're identical tuning forks, hitting one will create a sound wave that will propagate over and make the second tuning fork vibrate in unison. It's just an example of resonance. All musical instruments, whether they're strings that you pluck or bow, you blow into it, even a drum that you hit, those all use standing waves and resonance to produce different tones. So remember, what's next are the answers to the 3 questions that were asked during this. Highly recommend you try and work those questions out before you look at the answers, but those are what's next. Thank you for watching this video on Chapter 6 about waves.